Hello and welcome to today's lesson on contact and non-contact forces, which is part of the GCSE Combined Science topic of forces. So in today's lesson we're going to look at contact and non-contact forces. So we're going to try to understand what the different types of forces in the universe are. So if we've been successful and learnt in today's lesson, we should be able to state Newton's laws of motion, relate Newton's laws of motion to different situations, and finally understand the difference between contact and non-contact forces, which links into the following part of the GCSE Combined Science specification of physics in 6.5.1.2, contact and non-contact forces. So, we can demonstrate forces in many different situations, such as when an object is being pulled, such as when an object is being pushed, such as when an object is being accelerated, such as when an object is being stretched. Now there are many different examples of forces in the universe. These can include the electrostatic force, the gravitational force, the thrust force, tension, air resistance, the magnetic force, the frictional force, and the normal contact force. And so a force is a push or a pull that acts on an object due to the interaction with another object. The unit of force is the Newton, and all forces are vector quantities, so they must be given a magnitude and an associated direction. Now the following demonstration of a paperclip and a magnet and two magnets shows that forces can be non-contact. Objects do not have to be touching each other to exert a force on each other. Now examples include the gravitational force, the electrostatic force and the magnetic force. So for example, take the Earth and the Sun. The Earth and the Sun are not touching, but there's still a gravitational force between them, so this shows that the gravitational force is a non-contact force. But some forces do need to be in contact with each other to exist. Now we call these contact forces. So examples include friction, the reaction force and tension. So the ball and the surface in this example are rubbing against each other, and the bumps in each other prevents a smooth movement. So this contact provides the frictional force. In this example, the surface is providing an upward force on the ball to stop the ball falling through it and hitting the ground. So this contact provides the reaction force. In this example, the ball is pulling down on the cable. This causes the cable to stretch out. So this contact provides the tension or tensile force. So we can categorize all forces as either contact or non-contact forces. So these can include friction, air resistance, tension, the normal force. So these are contact forces, as these forces occur when objects are physically touching, whilst non-contact forces include the gravitational force, the magnetic force, the electrostatic force. So these forces can occur when objects are physically separated. So all forces between objects are either contact forces, forces that occur when the objects are physically touching. So examples of contact forces include friction, air resistance, tension and the normal force. But you can also have non-contact forces, forces that can occur when objects are physically separated. So examples of non-contact forces are the gravitational force, the electrostatic force and the magnetic force. So if objects do not have to be in contact with each other to exert a force, how do we represent the area in which a non-contact force can act, and what do we call this in physics? Well, this is indicated by something called a field. Objects can exert a non-contact force by exerting a field in space. A field is a region of space where a body can feel a non-contact force. For example, the Earth's gravitational field is a region of space where you can experience the Earth's gravitational force, and we represent these with field lines. Now the strength of a field line is given by its field density. How many field lines are found in an area, or how close the field lines are to each other. So, in a gravitational field, the closer you are to the object making the field, the denser the field lines, the stronger the non-contact force experienced. Now, in an electrical field, the closer you are to the object making the field, the closer the field lines are to each other, the stronger the non-contact force experienced. Now, interestingly, in an electrical field, the field lines point in the direction a positive charge will move in. So remember, the strength of a field is given by how many field lines you find in a particular area. This tells you how strong a magnet is. Now, understanding how forces interact with objects is very important, as it tells us how the object will behave in the universe. So for example, a pendulum can only be understood if the forces exerted by the pendulum are understood. So understanding the laws of forces allows physicists to understand and predict how objects will behave in the universe. So in 1687, Sir Isaac Newton devised 3 laws which dictate how all forces, contact or non-contact, interact in the universe. Now, for every single situation in the universe, you must consider obeying Newton's laws of motion. So we use Newton's laws of motion to predict how all objects will behave in the universe. So we can even use Newton's laws of motion to predict where the planets are and will be in the future. So this is how we can send spacecrafts to these planets to make measurements. So here are the 3 laws of motion. Law 1, the law of inertia. Every object stays at a constant velocity when there are balanced forces on the object. If there's a resultant force on the object, it will change either speed or direction. It will accelerate in the direction of the resultant force. Now, inertia is the idea that an object keeps at a constant velocity if there's no resultant force. This is the physics behind how objects can accelerate or why they have inertia. The Newton's second law is that resultant force in newtons equals mass in kilograms times by acceleration in meters per second squared. This is the physics behind how to calculate the acceleration experienced by an object. Whilst law 3 is that when 2 objects interact with each other, they always exert equal yet opposite forces of the same type on each other. This is the physics behind how 2 objects can interact to cause both of the objects to accelerate in the opposite direction to each other. So we have law 1, the law of inertia. Law 2, the resultant force equals mass times acceleration, and law 3, that when 2 objects interact with each other, they always exert equal yet opposite forces of the same type on each other. So we know that for Newton's first law, if there's no resultant force, there's no acceleration on the object. Now, there can still be movement with no resultant force, but there's just no acceleration. So the object moves at the same speed in the same direction, and this principle is called inertia. But if there is a resultant force, an object will accelerate, but the acceleration happens in the same direction as the resultant force. Now, to clarify, a resultant force is an overall force on an object. So a resultant force causes an acceleration. So in this case, we have a resultant force of 40 newtons. So the object will accelerate in the same direction as where there's a resultant force. Yet in this case, there's no resultant force. This means that there's no acceleration. The object stays at the same speed. Now, this concept is called inertia. Now, Newton's third law states that when 2 objects interact, they always exert equal and opposite forces of the same type on each other. So for an acceleration to occur, there needs to be a resultant force on the object, not pairs of objects. And this reaction force is only one force on the object. But if the forces on one object are the same, it would not accelerate. However, Newton's third law pair works on 2 objects, not one. So in this example of just having a ball, you can't get Newton's third law because 2 objects are needed to form a pair of forces. Now, in this case, we have 2 objects interacting, so the forces produced are due to Newton's third law. Now, the forces produced will be the same size, they will act in opposite directions, they will be of the same type, but they'll be acting on a different object. So this means each object would receive the same resultant force and will accelerate. But this tells you a very, very important idea, that even though they both have the same resultant force, the 2 objects do not need to accelerate at the same speed, as the acceleration depends on the mass and the resultant force. The more mass of the object, the lower the acceleration experienced by the object, whilst the less mass of the object, the higher the acceleration experienced by the object. So you can summarize Newton's third law pair forces with the following. They are the same size and are the same type, but they act on different directions and on different objects. So, a force is a push or a pull that acts on an object due to the interaction with another object. All forces are either contact forces, where the objects are physically touching, or non-contact forces, where the objects are physically separated. Examples of contact forces include friction, air resistance, tension, and the normal contact force. Examples of non-contact forces are the gravitational force, the electrostatic force, and the magnetic force. A force is a vector quantity, and you should be able to describe the interaction between pairs of objects which produce a force on each object, and the forces are to be represented as vectors. So if you've been successful and learned in today's lesson, you should be able to state Newton's laws of motion, relate Newton's laws of motion to different situations, and understand the difference between contact and non-contact forces. So I hope you've enjoyed today's lesson on contact and non-contact forces, which is part of the GCSE Combined Science topic of forces in GCSE AQA Physics. Thank you very much for watching today's lesson, and as always, have a lovely day.